Okay, so freezing point depression, boiling point elevation, these are related processes. If we look at a phase diagram, we see that the vapor pressure is lowered at all temperatures by adding a substance, a solute. Okay, we talked about that. I know it seems a long time ago. We talked about vapor pressure lowering. That when you add something to, say, water, it lowers the vapor pressure. Well, that vapor pressure is going to be lowered at all the temperatures. And so if we look at the phase diagram, we see that for a solution, it's going to move these phase transition lines out. And so what we find is for freezing, which is the point between the solid, up at 1 atmosphere, between a solid and a liquid, that due to the movement of this line, we have a freezing point at a lower temperature, freezing point, melting point, same thing. And this one moves to the right, and so the boiling point goes up. I remember as a student that I knew that they moved, but I had a hard time remembering which was elevation and which was depression. And so what I finally thought of to remember this is those points move away from each other. Okay, so the freezing point moves lower and the boiling point moves higher. And so what you have is it stays a liquid over a larger range of temperatures. So they move away from each other. Boiling point goes up, freezing point goes down. So the result of the vapor pressure lowering is the solution has a lower melting point and a higher boiling point than the pure solvent does. And so there's an equation for freezing point depression. Here, delta TF means the change in the freezing point. And unlike all the other places where we've used delta, where it was final minus initial, this is usually reported as a positive number. I don't agree with that, but it is, and we have to go along with what the other people say. So the change in the freezing point is equal to the molality of the solution times a constant. And this constant would depend on the solvent. So there's a constant for water, there's a constant for ethanol, etc. Molality is used here because molality doesn't change with temperature. Molarity changes slightly with temperature. So we have to use the molality. Molality is moles of solute per kilogram of solvent. So here's a table in your textbook, and this is showing several solvents that might be useful, and here's their freezing point depression constant, and here's their normal freezing point. And then we're also given the boiling point and the boiling point elevation constant because we're going to need those in a couple of slides. So for water freezes, come on, pointer. No? Yep, there. What? Okay, sorry. Water freezes at 0 degrees, and its freezing point depression constant is 1.86. The units on that are degrees Celsius per molal. So we can do a problem like this. Calculate the freezing point of a 2.6 molal aqueous sucrose solution. So we need the equation. The change in the freezing point is equal to the molality times the freezing point depression constant. The freezing point depression constant for water is 1.86 degrees Celsius per molal, and I really only remember that because we just looked at the slide. That's not something you would memorize. So we've got the molality that was given to us. So we can plug these in here and we get 2.6 molal times 1.86 degrees Celsius per molal, and the molalities cancel out. . and I'm getting 4.836 degrees Celsius, and sig figs would give me 4.8. Is that the freezing point of the solution? No. That's the change in the freezing point. Okay? So the question's asking, what is the freezing point? Well, what's the freezing point of the pure solvent? It's aqueous. Where does water freeze? There's our thermometer. What temperature does water freeze at? 0 degrees Celsius, thank you. And when you add something to a solution, does the freezing point go up or down? It goes down. And this is how much it went down. So our freezing point is 4.8 degrees lower than the freezing point of the pure solvent. So the freezing point then is what? It is really that simple. What's 0 minus 4.8? Negative 4.8. You guys awake? Yeah. Yes. 4.8 is a positive number, and I agree that that's wrong, but it's what everybody does. So delta is always final minus initial, except for freezing point depression. Sorry. Yeah. It will always go down, but it depends on what the initial freezing point was. So if your pure solvent froze at 50 degrees Celsius and it decreased by 4.8, then it's not going to be negative. It'll just go down. Yeah. So this is always calculated as a positive number, and I agree that's disturbing and confusing. I'm sorry. I apologize for the scientific community about that. Any other questions? And when we make ice cream today, we're going to use this equation. Instead of calculating the freezing point depression, we're going to calculate the molality of the salt solution. And sometimes students get a little carried away and they're like, well, molality is moles per kilogram of solvent, and so they're trying to use masses and stuff. And that's not what we're doing. We're going to measure the temperature of the saltwater ice solution, and it's going to be less than 0. It might be as low as negative 10 degrees Celsius. And the freezing point depression constant is this guy right here. And so if we know the change in the freezing point, then we can calculate the molality. And that's the only calculation we're doing in lab today. And we're going to eat ice cream to reward ourselves for that. Minus 4.8. So boiling point elevation works in the same way. The equation is the same, except we've got a subscript of B instead of F, B for boiling instead of F for freezing. So delta T is the change in the boiling point. This is going up, and it's positive, and we don't have an issue with it being positive here. It's the molality times the freezing point elevation constant. Boiling point elevation constant. And we have a photograph here of someone pouring antifreeze into the radiator of their car. So by adding the radiator fluid, this antifreeze, typically it's ethylene glycol, but there are other alternatives that are less dangerous to pets. By adding a solvent to the water, you raise the boiling point of the water and you lower the freezing point of the water. So if the water boils at 100 degrees Celsius, once it gets to that temperature, it's going to be turning into a gas and put a lot of pressure on your radiator, and the valve on your radiator lid should let that out, and you'll see big plumes of steam coming out from your car. Your car's overheating. This raises the boiling point of the water so that it can be effective at a higher temperature. And then it also, as the name suggests, prevents it from freezing. So we don't really have an issue with that here because it'll get below freezing, but not for very long, and certainly not long enough to freeze the water in your radiator. But where I grew up in Minnesota and Iowa, it gets really, really cold. They sometimes go for a couple of weeks in Minnesota where it doesn't get above freezing. And so the fluid in your radiator would freeze solid if you didn't have antifreeze. And when water freezes, it expands, and then it breaks things. And so that would be really bad. So, if you're having a car emergency and you need to fill up the radiator, you can use pure water to fill up the radiator, but that's only a temporary solution. You need to get somewhere to get some antifreeze, because around here we do care about the boiling point because it gets very warm. Anybody have any questions about that? Calculate the boiling point of a 3.6 molal aqueous sucrose solution. Well, we need the boiling point elevation equation. So the change in the boiling point is equal to molality times the boiling point elevation constant. I don't remember what that one was because I didn't really look at it when we had that slide. So let's go back here. So for water, boiling point elevation constant 0.512. So Kb equals 0.512 degrees Celsius per molal. How do I know that water is the solvent here? It says aqueous. Okay. So I'm handed the molality, 3.6 molal. They could make us calculate that, but they're tired of being mean. 0.512 degrees Celsius per molal. Those cancel out. And so this gives 1.8432 degrees Celsius. 3 sig figs, so 1.84. What's the boiling point? So this is the change in the boiling point. So we need to take the normal boiling point of water and add this. It's a thermometer. If it normally boils at 100 degrees Celsius, then this is making it go up. That's supposed to be an arrow. 1.84. So the boiling point is 101.84 degrees Celsius. Any questions? Yeah.
If the question didn't say it was aqueous, what would we use?
That's an excellent question. So if it didn't say aqueous, what would you do? It would have to tell you what the solvent was, or give you the constant that it was needed. Yeah. Any other questions? You could have to calculate the molality, yeah. But we practiced that already. Yeah. This is just another little piece that can be added to the other stuff. It's a little bit like learning a line dance or something, where you learn this particular step and you learn that step and you learn the other step. And that wasn't so bad, but now they want you to put them all together, and that's kind of hard to remember, right? So you have to practice the individual pieces, and that makes putting them together easier. (101.84). Okay, so another colligative property relates to osmosis. So So osmosis is the flow of solvent from a solution of lower concentration to one of higher concentration. And this is what makes seawater cause dehydration when you drink it. We talked about that, the nature's tendency towards mixing and entropy with the spreading out of energy. So a semi-permeable membrane is a membrane that is partially permeable. It allows some things to pass and others not to pass. And typically the solvent is allowed to go through and the solute is not. Biological cells are full of, literally, semi-permeable membranes. So we can construct what's called an osmosis cell. So here's a tube that's shaped like a U. We used to call those U-tubes, but now that means something else. And it's got a semi-permeable membrane in the middle here. So the two sides of the tube are separated by a semi-permeable membrane. And we can put a high solute concentration over here, so salt water, and then we can put just pure water on the other side. And so this is a bit like what would happen in your stomach, drinking seawater or in your intestines. The semi-permeable membrane here is like the cell walls in your body. And so osmosis is the process of the water molecules moving preferentially towards the concentrated solution. So we can think of this in a couple of different ways. I think the most straightforward one is just to think about a dynamic equilibrium. The water molecules can move both ways, and they will move both ways. But the ones coming from the salty solution going into the pure water solution, there are solute particles here that are getting in the way. And so the rate of water moving from the salty side to the pure side is slower than the other direction where there's nothing getting in the way. The water can go through the membrane and it's not impeded by anything. So because we have a higher rate of flow from the pure side to the salty side, we have a net flow of water to this side. And after a period of time, what we'll see is that the level of water on the salty side goes up, and the level of liquid on this side goes down. Any questions about that? So remember when we talked about gas laws, we looked at a manometer, which was mercury in a tube, and we could tell something about the difference in pressure between what was in the container and what was outside by looking at the difference in height of those columns. So here we have a difference in height. It's not mercury, it's water, but there's still a difference in the levels, and that is equivalent to a pressure. So this is the osmotic pressure. In order to prevent osmosis from happening, this is the pressure we would have to apply to this side to prevent osmosis from happening. So that's called the osmotic pressure. Any questions? Have you heard of reverse osmosis? Yeah, so that's a technique for purifying water. And literally what that is you've got a semi-permeable membrane, but you're making the osmosis go in the opposite direction. How do you do that? By putting pressure on this side. By putting pressure on this side, you can force the osmosis to happen in the other direction, in the reverse direction. And that causes you to get pure water. Essentially, the semi-permeable membrane is acting as a filter, and it's filtering out everything but the water. So osmotic pressure is the pressure required to stop osmosis, and it is given the symbol capital pi. So this is a capital pi. Capital pi is equal to the molarity times the ideal gas constant times the temperature in kelvins. So that's a capital M, that's molarity, as opposed to the other ones which were molality. The temperature has to be in kelvins, and we've got our familiar ideal gas constant, 0.08206 liter atmospheres per mole Kelvin. So calculate the osmotic pressure in atmospheres of a solution containing 1.5 grams of ethylene glycol in 50 milliliters of solution at 25 degrees Celsius. So this one's not as simple as the others because they're making us do some stuff before we use the equation. But the equation for osmotic pressure is it's the molality times the ideal gas constant times the temperature. So R is fine, we know what that is, 0.08206 liter atmospheres divided by moles times Kelvin. And the temperature needs to be in Kelvin. So we've got 25 degrees Celsius. So we convert that to Kelvin. But then we need the molarity. Molarity is moles per liter. So we've got 50 milliliters of solution. So we can convert that to liters. And that's going to be 0.0500 liters. And then we need the molarity, the moles. So we've got a mass, 1.56 grams. We need to convert this to moles. So 2 times 12.01 plus 6 times 1.008 plus 2 times 16, 62.068. So the grams cancel out. Zero 0.024 167 moles. I started with 3 significant figures in this measurement. My molar mass has more, and so my number of moles has 3 significant figures. Those leading zeros don't count. So I want to make sure I keep at least 3. 0.02467 moles. So I can take my moles and divide by the volume in liters. And 0.48334 moles per liter. Then I have this sense of accomplishment, but then I realize, oh, wait a minute, I'm not done. That was just a piece of it. So now we have the parts that we need. We've got the molarity, we've got the temperature, and we've got our ideal gas constant. So we can put these together in our equation. 0.48334 moles per liter. In an equation, it's better to use moles over liters instead of just the capital M, because it's easy to forget what the capital M stands for. And then it's hard to cancel out the units. Ideal gas constant, 0.08206. Liters times atmospheres divided by moles times kelvins. And then 298 Kelvin. So let's look at the units here. I've got moles canceling moles, and liters cancel liters, and Kelvin cancels Kelvin, leaving me with atmospheres. So 0.48334 times 0.08206 times 298. 11.819 or 11 point, I don't know where that came from, 11.8 atmospheres. Any questions? But that's a capital pi. It means osmotic pressure. It's not the 3.14159 blah 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 blah. Yeah. And when you write it out by hand, it's a little bit tricky. So we've got lowercase pi has that little tail on the front, and capital pi doesn't, and it's bigger. I mean, it's no worse than capital M versus lowercase m. We're just not used to seeing a capital pi, right? Any other questions? Yeah. Hang on just a minute. Okay.
Do you want us to know the conversions for millimeters mercury,
Yeah, I would expect you to remember how to convert atmospheres to torr or millimeters of mercury. That's the only pressure unit that I would expect you to remember. And that's the 1 to 760. 760 millimeters of mercury is in the atmosphere. So is 11.8 atmospheres a high pressure? Yeah. It's almost 12 times normal atmospheric pressure. Now, we are accustomed to 1 atmosphere of pressure, so we don't feel it at all. But you multiply that by 12, and that's pretty hefty. That's a big, big pressure.